Okay, thank you. Can you hear me? Okay, good. So first, let me say today's topic, it may not be my original topic, but we just use it, small gaps between prime numbers. Yeah, we know what is a prime number, right? So let's see. A prime number, let me say it quickly, but usually here, by definition, a prime number should be greater than 1. 1 itself is not a prime number. So greater than 1, which is only divisible by 1 and itself. For example, like 2, 3, 5, 7, 11, 13, 17, 19, but not 21, right? So these are prime numbers. Simply, we just say the primes. And also, about the prime numbers, we know a very fundamental result, the so-called fundamental theorem of arithmetic. Every integer greater than 1, maybe itself is a prime number, or it is uniquely is a product of several prime numbers. Always like this. In other words, we say every integer greater than 1 has a prime number as its factor, right? So now about the prime numbers, we may ask many questions. We may say, by definition, a prime number is easy to understand. Yes, but in number theory, there is such a sentence. Why prime numbers are very difficult to handle, to study? Because except for the definition, we know nothing else. So, okay. So first, a question, very natural question. Totally in the world, under the sky, in the whole universal, how many prime numbers? How many? Maybe 1 million, 1 billion, maybe very large, but totally how many? This question was answered, that should be 23 years ago, 100 years ago by Euclid. We know Euclid is very famous in geometry, right? But also, his way, maybe like the so-called method of proof by contradiction, was first introduced by himself, or maybe he proved one theorem. There are infinitely many prime numbers. And let's recall the proof. I think many of us know how to prove it by contradiction. So we assume there are only finitely many prime numbers. Then we can give a list. We say they are, give a list. First is P1 equal to 2, second P2 equal to 3, then always there is the largest one is P sub n. Okay, thank you. So, yeah, totally. These are all prime numbers. Now we take the product of all these numbers. Then the product plus 1, we get a new integer. This integer could be very large, but it is a finite number. It's an integer. Then we can find that this integer is not divisible by any of P1, P2, Pn. Say P1 equal to 2, then 2 times everything is an even number. Even number plus 1 is not divisible by 2. Then P2 is 3. This is the multiple of 3. Multiple of 3 plus 1 is not divisible by 3. So this number is not divisible by any of a prime number. That's a contradiction. So either it is a prime number, but this prime number cannot be equal to this, or it is a product of, it has a prime number factor which is not equal to P1, P2, Pn. So we cannot have only finitely many prime numbers. That's Euclid's proof. And the next, we say the distribution of prime numbers. So because it is very difficult to handle, except for its original definition, the definition is simple. So now it is still a major topic in modern number theory. There are many interesting and unsolved problems in this field, but there is a feature of these problems which looks very simple and can be explained to the beginning to high school, middle school students very easy. Let me show one example, the so-called twin prime conjecture. We say a pair of prime numbers, we say P, Q. It is said to be a twin if the larger one is equal to P plus 2. So let's look at how many twin prime pairs. Look less than 100. We give the list 3, 5, 5, 7, 11, 1, 2, 3, 4, 5, 6, 7, 8. Then we may ask totally how many pairs of twin prime numbers. Now it's difficult to handle. Of course, we may use a computer program less than 1 million, less than 1 billion. Till now, I don't know what should be the record on the anyway, people already found many twin prime pairs. Then there is a conjecture, the so-called twin prime conjecture, that asserts that there are infinitely many twin prime pairs. Then let me say that the study that should be around maybe less than 100 years ago, first by a Norway mathematician whose name is Brun. I don't know how to pronounce it in Norway language. He discovered a very novel method toward the twin prime pairs and some other numbers in primes. Then he made a very significant contribution toward this conjecture. And also many mathematicians did a lot of things. A number of partial results have been obtained, but till now, this is still an open problem. And even till now, if you ask me to predict how many years, maybe within 10 years, 20 years, 30 years, I said I'm unable to predict it. We know some very essential problem, essential, difficult, something like this. So in particular, until recently, we had not been able to prove that we said the gap between two primes is equal to 2. Then let's consider something weaker questions. Maybe how many prime pairs the gap is, maybe it's not 2, but less than or equal to 4, less than or equal to 6, maybe less than equal to 100, 1 million. Can we prove there are infinitely many pairs of the primes such that the gap is less than a certain number, a finite number? So this even today is, I remember that was 3 years ago in April 17th. Also 3 days ago, I submit my paper to the Annals of Mathematics. So just 3 years ago, before that time, even no one could prove that. Now let me give an indication of how 3 years ago I was able to prove a result. The statement now it says there are infinitely many pairs of prime numbers, we say also PQ, such that the gap between these two numbers, of course, P is not the same as Q. So the gap is greater than 0, but it is strictly less than a certain constant. That is 70 million. This number is very large, but the first time we get an upper bound. Before that, before the 70 million, previous result is Q minus P is less than infinity. But that was trivial, right? So now we are given a certain, which is the weak form of the twin prime conjecture. Now, I know this should be like a public talk or something. Anyway, so I would like to indicate them the basic idea, but maybe my way is pure in mathematics. But let me say something, which the number theory, the study, somewhat it is said is similar to physics or some other natural sciences. Like the experimental sciences, we need to do some experiments. But here, what's the experiments? The objects of the experiments are not atoms, not nuclear something. That should be something like the numbers, quantities. Also, we may say functions or something. So now we try to make a formulation of the problem. How can we approach the twin prime or the prime pairs, the bounded gaps between prime pairs? We try to introduce a function first. Now let's see for each positive integer n, we say the row of n is such a function that takes exactly two values. Either it is equal to 1 if n is a prime number. Otherwise, it is 0 if n is not a prime number. So we see that a row of 2 of 3 of these are all prime numbers. So row of these values equal to 1. 1 for even this you may verify which is not a prime number. That is not either. These are not prime numbers. So the row value is equal to 0. Now we may ask a question, do you think this function is simple? Just like the definition of prime numbers, the definition is simple. And it only takes two values. But to handle it, something should be not simple, very difficult. Let's see. Now, why I introduce such a function? It is due to a simple factor, the following simple factor. I should put the following. That's okay. For any positive integer n, row of n multiplied by row of n plus 2 equal to what? It also takes just exactly two possible values. It is equal to 1. It is equal to 1 just means each factor is 1. Row of n is 1, is equal to 1. So n is a prime number. Meanwhile, row of n plus 2 is also equal to 1, right? So n plus 2 is also a prime number. So this function takes value, this product takes the value 1 exactly when both n and n plus 2 are prime numbers. Otherwise, it is 0. So that's why we say the twin prime conjecture is to show that this equal to 1 for infinitely many n. That means we have infinitely many twin prime pairs. In other words, let's take the sum. With small m add to 1, starting from 1, until to a very large number, capital N, the sum. Then as capital N getting larger, 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 this contains more and more twin prime pairs. So if totally there are infinitely many, this sum tends to infinity. So this is the first attempt we try to formulate the twin prime using the sum, your function, something like this, to do that. But how can we do that? How can we, I say we put a limit, capital N approaching infinity equal to infinity. Till now, we are unable to handle it because we say prime numbers look simple, but whenever we consider a product like this form, almost right now we are able to handle it. are difficult. Why? Let's consider something else. We're not going to take the sum, take the product. Instead, let's consider the sum of these two terms. This could be a little easier, much easier to handle. Now, the twin prime conjecture is equivalent to rho of n plus 2 is equal to 2. Infinitely often. That should be. That means because each term is at most is equal to 1. If the sum is equal to 2, then this must be equal to 1. That must be also is equal to 1. That gives us a twin prime pair, right? So it's infinitely often. But let me just rewrite it a little, because this takes the values just either it is 2, or maybe 1, it is equal to 1, or maybe it is equal to 0. For most n, it is equal to 0. So if we can prove this inequality infinitely often, minus 1 is greater than 0, so minus 1 is at least 1. It's just like this. Now the next. The next, we come to the mathematics, the experiments of mathematics, not physics, not chemistry. We are looking for if we can find some non-negative, just usual numbers, even not integers, could be 1/2 or something, Cn, such that for any large capital N, the summation is n is from capital N to 2 capital N something. This is positive. Then this is, we say a sum is positive implies that at least one term is positive, right? So this implies that there exists at least one term in this sum, which is strictly positive. But this is positive under the coefficient C sub n is non-negative, but the product is positive. So C sub n must be also positive, cannot not be 0. So the result is for such an n, this is greater than 0. So that n and n plus 2 form a twin prime pair. But now, because the sum is from capital N to 2 capital N, so this n is greater than capital N, and the capital N can be arbitrarily large. So for every capital N, always there is a twin prime pair which is greater than capital N. Therefore, the conclusion, there are infinitely many twin prime pairs. So can we prove something like this? Now the question, what remains is about, we say the coefficients, C sub n. We only have one constraint. C sub n must be non-negative, greater than or equal to 0. Then how can we look at, in a Chinese words, we may say this looks like seeking a needle under the ocean, right? A very small needle, we try to find it in the ocean. How can we do that? So the statement is just like this, like at the very beginning what we said. Primes are very simple by definition. Yes. This looks, if we can find some the C sub n, something such that this is positive. But in practice, still it is very difficult. What I can say is we cannot choose very simple values of C sub n. C sub n equal to 1, C sub n equal to n, C sub n equal to n square equal to... You may try, but what I can tell, that never works. Usually we choose some C sub n. We find the sum like this. It is negative, not positive.
Why do you include 0 as a possibility for C sub n? Is that important?
What?
Why is C sub n 0 also considered? Is that important? Or?
This is important. Yeah. Okay. So let me say till now, sorry, let's come back. One more about this formula. Still, this is a possible way to eventually to approach the twin prime conjecture. And the condition, by conjecture, we may consider some possible choices of the C sub n equal to this one, takes this form, that form. But till now, still we are unable to prove this. So now we try to prove a weaker result, the so-called bounded gaps. This one is what I said earlier. Like in modern number theory, solutions of many problems are reduced to finding some numbers C sub n such that a certain relation, like the formula 2, holds. Meanwhile, the C sub n should satisfy certain constraints, such as the so-called non-negative conditions. But usually it is very difficult. Let me say, I mentioned earlier that was in 1914, this is almost just 100 years ago. The Norway mathematician Braun introduced this method. He chose the C sub n satisfying the non-negative condition, but it was very difficult, very complicated. Then the construction of the C sub n is often technical, and in many cases, the optimal choices of C sub n, we don't know how to choose it. We just try something by experiments. But one thing, in most cases, we need the C sub n, we have a constraint. It should be non-negative. Then another also is a Norway mathematician whose name was Selberg in 1950. He found that one way. He started with a very arbitrary real numbers dn. Then he took C sub n equal to the square of another number. The square of a real number naturally satisfies the non-negative condition. Actually, this idea till now, still we follow it. But also we may ask, is this the best choice? Do we have something better than this? What I can say is only it's possible, but I don't know how to choose that. So now let's come back to the weak form 1. Let me recall it a little. Yeah, the so-called bounded gaps less than 70 milli. And before my work, these three mathematicians, he is in the United States, California, just in San Jose State University. He is in Hungary and he is in Turkey. These three mathematicians, they had spent maybe 20 years toward this twin prime, and they get an idea, something. We consider a set of integers satisfying certain admissible conditions. This it's so technical, I'm not going to say. I follow their way, start with a set of integers. But in my work, I make my own choice, which is admissible to my work. I choose k is equal to 3.5 million. And starting with the h1 is 0, so these are just greater than, just in this way, increasing. And the maximum is less than 70 million. Then to prove the bounded gaps less than 70 million, we just need to show that for infinitely many n, the k turbo, the k numbers, n plus h1, n plus h2, these k numbers, this turbo, we say, contains at least 2 prime numbers. So we say one is a prime number, another is a prime number. And these two numbers, of course, are distinct, not the same by that condition. And the gap between these two prime numbers at most is less than 70 million. So we need to prove now our ways to show that for infinitely many n, these k numbers in this sequence contains at least two prime numbers. Then we take the formulation like this. It's the same as precisely. Sorry, that should be Jie from, I skipped it for typing error. This Jie starting from 1 to k. Okay, I missed it, sorry. So we need to prove this. Further, how to prove that is for infinitely many n, the sum above it is positive. Then we need to show for all large capital N, there is a n greater than capital N such that the 3 hold. 3 is just the previous one, the last one here. To prove this, the idea are the same as before. We choose non-negative numbers, C sub capital N, something like this. We have a non-negative condition and show that for all large n, this sum is positive. Then we repeated what we did before. It is positive, at least one term is positive. Then we skipped this one because C sub n also should be positive. Just means the large brackets here is positive. Then that just means there are two prime numbers at least. So that's the gap. So now we fix the H1, H2, HK. And what remains is we need to choose the coefficients C sub n satisfying this condition. And we need to verify this is correct. Now the question, how to choose the C sub n by experiments. Till now, what I like to say is, this is just the beginning of a new approach, not only for the twin prime, for other number theory problems. Just the beginning of a new approach. There are still lots of things remaining open. We don't know how to choose it. We just get something very. No, in myself, I do not think these results are very good. We still have a lot of things to do. Now, I mentioned that that was the previous work of these three mathematicians. They found that the appropriate choices of the Cn, that is, which are of the form. First, we say it is a square of something else. So non-negative condition, we don't worry. And that is the D. The D divides the P of n. That's so complicated. And the D has like a restriction. D is less than another value is capital D. Here, I apologize. It should not be X. This should be the capital N, not X. Sorry about that. That's a typo. So, and here we have a logarithms factor, the power of a logarithm. We have another factor which is mu of D. Let me explain. Here, G is a certain positive integer, which is a constant. In my paper, I talk maybe G is equal to like the 200 or something. Anyway, it is a certain fixed number. And mu of D is a very common function in number theory, the so-called Mobius function. The definition is mu of 1 is equal to 1. Mu of D, if D is the product of distinct prime numbers, say we have totally r distinct prime numbers, factors, then mu takes the value -1 raised to r. For example, mu of 6 6 equal to 2 times 3, right? The two distinct prime factors. So r equal to 2. Therefore, mu of 6 is equal to minus 1 raised to 2. It is equal to 1. But how about mu of 4? 4, of course, is a product of prime numbers, but they cannot be distinct. 4 equal to 2 times 2. That's not the distinct situation. Otherwise, mu of 4 is equal to 0. Then the evaluation of the sum S given in 4. That is, we say, let me just add some comments. Also, that's the so-called why we say the number theory is similar to some experimental sciences. Usually we introduce the coefficient like this. Of course, it also depends on a lot of things. Here we have a capital D, which is the power of n. The exponent is b. b is a constant between 0 and 1/2. Then the choice of n, actually, it depends on many, many quantities. Then how can we evaluate this sum? Usually, not like we just evaluate an integral. It is strictly equal to this one, equal to, then the integral of x squared is equal to 1/3 x cubed, maybe plus a constant. Here, we cannot have an explicit result of such a sum, because the sum itself is so complicated, right? But also, like doing some experiments, usually, always the sums in our process, the evaluation, yields a relation like this. S is equal to m plus e. Here, the capital M, here it is, my words could be a little rough. It represents the main term for the sum. But we cannot avoid, because the distribution of prime numbers are very irregular. So we always have some arrows. Then E represents the arrow terms. There is an explicit expression for the main term M, but it is also complicated. That involves many quantities. On the other hand, the arrow term, we can only obtain upper bounds for the absolute value of the arrow term. That is, we say, if we are doing one experiment, we get the result of what we claimed. But if we cannot, we are unable to control the contribution from the arrows. We cannot show the arrows is reasonably small. Still, do you think this experiment is reasonable? Still, we are unable to do it. Now, in mathematics, we say in order that S is equal to the main plus arrow. So in order to prove that S is positive, we just say the main term is greater than the we just need to prove the main term is greater than the arrow term in absolute value. Then the sum, it is positive, definitely. So now the next, what I like to say is the result of Goldstone, Pince, and Yitang. They make the choice of the coefficients Cn, and their result is find that the main term is very close to the arrow term. And in particular, they were able to show that the main term is positive. Otherwise, we can do nothing. However, there is a very essential obstacle on the estimation of the arrow term. They were unable to complete the proof. Now, what means the estimation of the E? That was, let's recall that here D is equal to capital N raised to B, depending on the exponent B. So this is relative to another big topic, the so-called distribution of prime numbers in arithmetic progressions. Let's recall that the exponent b appearing in 5. Using the classical estimate, that was the so-called Bambir-Vinogradov theorem. That was a classical theorem in the distribution of prime numbers in arithmetic progressions. That was in 1965. That was regarded as the best result. It's almost equivalent to the Riemann hypothesis. And also Bambir obtained the Fields Prize, not a Nobel Prize, because of his contribution in this way. But even such a strong result applied, they can only give an efficient boundary for the error term E. Required the B should be less than 1/4. However, the proof of 6 requires an efficient upper bound for E with some B is greater than 1/4. Let me just insert some words about that. That was in 2008 in the American Institute of Mathematics in the Bay Area, also in California. There was a workshop, and many mathematicians together, using 1 week, tried to say, can we get an efficient upper bound for E with some B greater than 1/4, maybe just 1/4 plus a very small number epsilon. That's enough. But eventually the conclusion was that no one could prove it. This, we know in number theory, we heard something about the Riemann hypothesis. To break the 1/4, should we get something stronger than the Riemann hypothesis? But I didn't, how to tell, I didn't hear the story about the workshop in 2008. So no one said, they said, no, we cannot prove it. We're unable to prove it. But I didn't know that. Then I tried to prove it. After 2008, I started maybe 2010. Then this was achieved in my paper using various tools from modern number theory. And also, actually, that is a very normal part of my paper. A number of innovations were introduced. In particular, I also used some deeper result, not from the number theory, rather from another subject in mathematics, algebraic geometry. Then let me say again, because someone may ask me a question, why you choose the 70 million? First, let me say this number has no special meaning. If I choose the 100 million or 120 million, that also works. But at that time, I tried to get a bound as small as possible. But because I was so tired at that time, really tired, I just say, just very roughly by calculation, using this way, so that should be this, if maybe 10 million is good enough. By that step, that should be 30 million should be good enough. Eventually, I determined 70 million. That satisfies every conditions. So I choose that number. No special meaning. Then also in my paper, in the first section, my introduction, I said, to replace this number by a value as small as possible is an open problem that will not be discussed in this paper. But later on, since that time, that was discussed by many other papers. In particular, today, 70 million has been reduced to 246. But till now, all these methods, what I can tell, reduced to 2. That means the final solution of the twin prime conjecture by the present methods still, I think, we have some essential difficulties. Thank you.
Allow some questions. Perhaps I could ask the first question. Could you give physicists at least some feeling why geometry comes in abstract geometry?
Oh, that is very indirectly comes. That gives an inequality. That is very precise an inequality. Then the primes using, after many reductions, it's reduced to estimate certain sums to find the upper bound. But at least one inequality coming from the algebraic geometry works. No.
They must have made a mistake, right? Because you said, I understood you to say that they had thought that if beep was bigger than a quarter,
Yeah.
it would be stronger than the Riemann hypothesis.
That was realized that somewhat, in some aspect, not totally stronger than, at least this does not imply the Riemann hypothesis. In some applications, so in some aspects, this should be stronger than the Riemann hypothesis. And Riemann hypothesis can only imply the result with B less than or equal to 1/4. But we need something with B greater than 1/4.
So your method of proof doesn't say anything about the Riemann hypothesis?
I didn't mention. And then later on, someone told me you should mention it, but it was too late, maybe.
Is there a connection? Is it true that there's some implication for the Riemann hypothesis?
No, it not. I said in some applications, Riemann hypothesis, assuming Riemann hypothesis, we can only achieve 1/4. But now, without using Riemann hypothesis, I get something greater than 1/4. But here I used the algebraic geometry. That was another Riemann hypothesis in algebraic geometry. And that Riemann hypothesis had been proved and also had been used in my paper. That's the so-called Riemann hypothesis over finite fields, something like this. These formulas?
The formula for C sub n involving Colloquia's function.
It's difficult. It's not very obvious. What I can say is that for some historical reasons, the mathematicians had done many experiments. They find maybe this form is good in some problems. But as I mentioned, still till now, I don't know. No one knows. Is this the best one? Can we find something better? I don't know. It's not obvious. Not outside. Still, the results are still in number theory. I use some tools from outside the number theory.
How did people get it from 70 million down to 246?
And first,
Was there any new method?
there are some new methods, some different choices of the Cn, and also finally the 246 strongly relies on the computer programs. They have to do lots of numerical things.
Are there similar theorems for distributions or half distributions, triplets, more than two?
Not very similar. We may say, yeah, there's something, but not very similar, we can say. Right. Yes. Yes.
No, my question is, was it 246 at any minute? He already gave an answer.
What I can say is the 246 may be further reduced. I myself know something, but maybe it's so complicated. But still, we are unable to achieve finally the 2. But we know the 0 is trivial, right? The gap is 0 is trivial.
Gary? Great. Sorry. You mentioned, well, I'll just say, some of the forms in your work, your talk, these product of the row functions, resemble in a vague way the Hamiltonian of one-dimensional spin chains. That is, they're products of spins, and the coefficients, even though the coefficient is on the sum, there are certain ways to reduce the spins into sums. There's a whole industry that does things like that. But I'm just making a vague resemblance to physics problems where people have used renormalization ideas. They map a block of spins into a block of a different size. And the fact you're taking blocks which are, let's say, size twice as big as an n, well, size n, and then looking at that suggests, I don't know, some connections to physical ideas that people.
Yeah, this makes certain suggestions. What I can say, maybe for these things, we just say some expressions in number theory. Even sometimes I have the feeling are somewhat similar to something like the Sturm theorem in physics, right? But let me mention one thing. The distribution of the Riemann zeta function, the zeros of the Riemann zeta functions, on assuming the Riemann hypothesis, also, of course, what we can find that the distribution of the zeros are very similar to what's the model, some U O square, something, a model in physics. We know that the numerical evidence tells that very precisely, but theoretically, I think this is still a very big mystery. No one could give a theoretical explanation. Why? Riemann zeta functions, the primes, has something to do with the physics. Very similar numerically, it's almost no error. Error almost is 0, right? I just mentioned it. Yes. At least it may not work directly. I don't know, but still, to my feeling, it should be completely open. Why the physics number theory has something looks very similar? Yeah, I didn't explain one thing. There is a just very essential problem. That's called the sort of parity problem in sieve method. We cannot avoid this one, so still it cannot reach the 2. Parity, but it's difficult to explain here.
But isn't it true that if there are infinite